In today's lesson, we're going to be looking at the chain rule. So the motivation for the chain rule here, let's take a look at the following example. If I look at this function here, notice that this function, you cannot solve this using the power rule. Notice to use the power rule, we would have to have x to the power of n, where n is any real number. Well, we have this expressed, the exponent's a real number, it's a half, but we don't have it expressed as x to the power of some exponent. We have here 2x squared plus 3. So power rule doesn't apply. Similarly, we cannot solve it using the product rule. Notice for the product rule, you need the product of two different functions here, and we do not have that. And lastly, also, the sum and difference rule also does not apply, as our function is not expressed as a sum or difference of other functions. And lastly, this function cannot be taken the derivative of by using the quotient rule, as we do not have the division of two different functions. And even if we did have the division of two different functions, or we had the plus or minus of two different functions, or the product of two different functions, at the end of that, when you go to take the actual derivative itself, it still is not expressed as a single variable to the power of n, and therefore the power rule would not apply. Let's go ahead and look at the chain rule. What the chain rule says is if you have two functions, let's say f and g, and those two functions are differentiable, then if you define f at x to be the composition of those functions, so in this case f composite g at x, it turns out the derivative of that function f prime is going to be the derivative of f prime at x times the derivative of the inside g prime at x. Let's look at some examples. For our first example here, you can take a look at this function. This looks a lot like the power rule. The only issue is that we have this expression here, x squared plus 4x plus 6 in there. So what's going on here is what we want to do here is this is really a composition of functions, in that if I define f at x to be x to the power of 5, and I define g at x to be x squared plus 4x plus 6, we can see here that f composite g at x would actually be equal to x squared plus 4x plus 6 to the power of 5. So this is a chain rule question. And the easiest way to apply the chain rule is to say, okay, suppose that this was just an x, how would I take my derivative? If I go to take my dy dx here, how the chain rule works is we're going to go ahead and take our derivative, but I'm just going to leave the inside unchanged. I'm going to take it as if it was just an x, but this is not the case. I did not have just an x there, so now I have to take the derivative of the inside. This would match your g prime at x. And in this situation here, the derivative of the inside would be times 2x plus 4. Notice here, this is your f prime at g at x, and this is the derivative of the inside, which is g prime at x. So the derivative of x squared plus 4x plus 6, all to the power of 5, would be equal to 5 times x squared plus 4x plus 6 to the power of 4 times the derivative of the inside, which is 2x plus 4. Let's try another. For this question here, let's first write this in exponential form. So this will be y equals 1 plus x cubed to the power of a third. Now, had this just been an x inside, we could apply our power rule directly, drop down the third, subtract 1, and we'd be done. What we're going to do here is, again, using the chain rule, we go ahead and take the derivative as if this was the power rule. So in which case this would be 1/3, 1 plus x cubed, 1/3 minus 1 is negative 2/3. And now we're going to go ahead and take the derivative of the inside. This is applying the chain rule here. The derivative of 1 is 0, and the derivative of x cubed is 3x squared. So now dy dx is going to equal 1/3, 1 plus x cubed to the negative 2/3 times 3x squared. We can simplify this a bit. A third and 3 will cancel off, and we end up getting here dy dx is going to equal x squared over 1 plus x cubed squared to the third root. So this is the derivative of our function here using the chain rule. If you'll notice what's going on is we have our function f at x is x to the power of a third, and our function g at x is 1 plus x cubed. So this is f composite g at x here. This is going to be f prime at g at x, and this is going to be g prime at x. And that's the application of the chain rule. Let's look at another question. So for this question here, there's a couple ways you can approach this. One way you can approach it, and this is the most common technique, is to rewrite this as t squared minus 2t minus 5 to the power of negative 4. Now notice that this resembles the power rule very closely. The only difference is the inside is not just a t, it's a t squared minus 2t minus 5. So let's go ahead and apply our chain rule here. So applying the chain rule, we take our derivative normally, and then we subtract 1, giving us -5. Now again, this was not just a t. This was a t squared minus 2t minus 5. I now must take the derivative of the inside, in which case this is 2t minus 2. Cleaning this up here, we end up getting -4 times 2t minus 2. Bring that back to the bottom, and we can do a little bit of simplification. I can factor out a 2 here. We get -8 t minus 1 over t squared minus 2t minus 5 to the power of 5. And this would be method number 1. Let's take a look at the next method of calculating the derivative of this example. Another way we could have done this question is to take a look at the question and say, okay, this looks a lot like the quotient rule. We have a function on the top and a function on the bottom. Well, if I want to solve this here, what I can do is using the quotient rule, let's go ahead and do that. We're going to go ahead and take our dy dx, it's going to be the bottom, times the derivative of the top is just 0, minus the top, which is just 1, times the derivative of the bottom. Now, when you go to apply the derivative of the bottom, now you're going to have to go ahead and use the chain rule. I'm going to drop down that 4, take the derivative as if this was just the power rule, make that a 3, and I take the derivative of the inside, which is 2t minus 2, and you take that entire expression and you divide that by t squared minus 2t minus 5, all squared will give that to the power of 8 now. Now we do some simplification. We can see here that this just goes all to 0, and continuing on here, you've got here -4. I can factor 2 out here, so that's going to end up being -8 t squared minus 2t minus 5 to the power of 3 times t minus 1, the entire expression, divided by t squared minus 2t minus 5 to the power of 8. Continuing on here, we can see this will cancel, and that'll reduce to become a 5, and our derivative is -8 t minus 1 over t squared minus 2t minus 5 to the power of 5. And we get the same answer as we got in the previous method. So it's up to you which method you want to use. The previous one is more commonly used, but just to show you, you can actually treat this as the quotient rule instead of the power rule. All right, let's try another. So for this next example here, we have the product rule here. This is my first function. This is my second function. So that's the main technique we're going to use here is the product rule. When I go to take my derivative, g prime at x, we're going to go here first. Times I go to take the derivative of the second, we got to use the chain rule. You drop down the 12, take the derivative as if it was just an x inside of here. We subtract 1, and then you take the derivative of the inside is going to be 10x minus 1. So that's going to be the first times the derivative of the second plus the second, so jot that down, times the derivative of the first. I'm going to have to go ahead and do the chain rule again. This will be 10 times 3x minus 2 to the power of 9 this time, and then the derivative of the inside is going to be a 3. Let's take a look at simplifying this question a bit. Notice I have in both expressions, I have a 3x minus 2 and a 3x minus 2 factor. So I can actually take out 3x minus 2 to the power of 9 out of this. Notice I also have a 5x squared minus x plus 1 to the power of 11 to the power of 12. So I can take out a 5x squared minus x plus 1 to the power of 11. And lastly, I have a coefficient of 12 here and a coefficient of 30. The greatest common divisor of 12 and 30 is going to be 6. So I can actually factor a 6 out of here as well. So what am I left with? Well, 12 divided by 6 is 2. I had 10 of the 3x minus 2's. I took 9 out. So I'm just left with a 3x minus 2. I had 11 of the quadratic here, and I took it all out, so that's gone. And then lastly, I'm left with the 10x minus 1. In the next term here, I had a 30, and I divided out a 6, so I'm left with a 5. I had 9 of these and took them all out, and I had 12 of these, so I'm left with 1 of these here, giving me the 5x squared minus x plus 1. So continuing on here, simplify our expression. We have 6 times 3x minus 2 to the power of 9 times 5x squared minus x plus 1 to the power of 11. I'm going to go ahead and expand all this out here. When I expand all this out, take a look here what we get here. If I expand this quadratic out right here, 30x squared minus 3x minus 20x plus 2, which will become 30x squared minus 23x plus 2. So now if you take a look here, I'm going to go ahead and double that. So when I distribute that 2 here, we're going to get 60x squared minus 46x plus 4. Now distributing the 5 into the trinomial, I get plus 25x squared minus 5x plus 5. Continuing on here, we have 6 times 3x minus 2 to the power of 9, 5x squared minus x plus 1 to the power of 11. And simplifying this some more, we've got 60x squared and 25x squared becomes 85x squared. We also have minus 46x and minus 5x, minus 51x, and then we have our plus 9. A quick discriminant check on this quadratic and this quadratic will yield complex roots, so we know we are fully factored in terms of the real number system, and we are done. Let's look at another question. So for this question here, again, always write it in its radical form so you can kind of see what to do here. And we'll notice as I look at this question, the main rule that comes to mind here is the power rule. If I view this as just a t, you can directly use the power rule. So let's go ahead and do that. I'm going to take s prime at t. We're going to go ahead and drop down the quarter and write down inside. Now, again, I'm treating this as if this was just a variable of t, in which case this would be my answer. But it's not. So by the chain rule, I now have to take the derivative of the inside. And now the derivative of the inside, if you're asked to take the derivative of this, you would then have to use the quotient rule, in which case we're going to do the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. So now we get s prime at t is going to equal 1/4 t cubed plus 1 over t cubed minus 1 to the negative 3/4 times. At this point here, I would expand everything out. Expanding out here, I get 3t to the 5th minus 3t squared minus 3t to the 5th minus 3t squared all over t cubed minus 1 squared. Continuing, we get 1/4. Let's go ahead and write this out. You'll notice here that the t to the 5's cancel. And collecting this up here, we get negative 6t squared over t cubed minus 1 squared. At this point here, there's not a lot that you can do to simplify the function. You do have a t cubed minus 1 to the power of 2 here. And with this negative exponent, you could flip it and have a t cubed minus 1 in the numerator. You could get some cancellation, but you'll still be left with a messy fraction, as you'd have to do 3/4 minus 2. So at this point here, I would leave the function as is. All right, let's look at another. So for this question here, if you take a look, we want to write this out in exponential form. We're going to have x plus x to the 1/2 and the whole thing to the 1/2. Now again, this looks a lot like the power rule, where this x plus root x is just being treated as a single variable here. I go to take my dy dx. We can go ahead and drop that down, and we can leave this unchanged. Subtract the 1, we end up getting negative 1/2. Now again, I have to take the derivative of the inside. And the derivative of the inside will be 1 plus 1/2 x to the minus 1/2. And that's the chain rule portion right here, where you take your derivative of your function, assuming this is just the power rule. It was not just the power rule, it's not just an x. You have to take the derivative of the inside, and you get this expression here. All right, let's look at another. So for the last example here, they give you some information. They give you a function, going to be f at x composite g at x. And you know all this information. I know g at 3 is 6, g prime at 3 is 4, f prime at 3 is 2, and f prime at 6 is 7. Let's go ahead and try to find what f prime at 3 is. Well, by definition, f prime at 3 is going to be what? Well, it's going to be f prime at g at 3 times g prime at 3. And that's our definition of the chain rule. Take the derivative of f prime at g at x times the derivative of the inside, which would be g prime at x. I applied that all at 3. So in this case here, this is going to be f prime. We know g at 3 is 6, and I know g prime at 3, I already know that value. Well, f prime at 6 is going to be equal to 7, and g prime at 3 is going to be equal to 4, and we end up getting 28 here. Okay, that concludes our lesson for the chain rule.